Yes, I think so. Please do, because I think your presentation will set the background nicely for the two.
Yeah. So welcome to the GCC seminar from around the world. This time we got 3 presenters from 3 places, from 3 continents, so that's pretty good. We hope it all hangs together. And what we decided to do was the start of the SAG conference in September. The first 3 papers were these 3 papers on autogenous grinding. And it really linked together nicely kind of the rethinking of autogenous grinding. So I thought, most of the GCC members didn't make it to the SAG conference. So it should be interesting to present them again. So you should be familiar with me. And Guillaume is from SGS in Canada, and he conducted the transport work in the pilot mill. I was going to say with me, but I was on another continent. It was during COVID and I couldn't be there. So I explained to him our objectives, and then he masterfully executed and modified the experiment. And it's novel. It's never been done before. So that's really good context where it is. And then Aubrey's going to look at an application with really soft ore. And can you make an ag mill work with a really low competence ore? And fascinatingly, I've had 3 examples just recently. So really interesting how this is linked together. And the other really interesting part for me presenting now is I'm in Boliden in Sweden, and they've got to be the world leaders in ag milling. So it's really good to be on home turf, should we say, of where ag mills are king. Boliden exclusively has ag and pebble milling. So it's really nice to be doing it here. I'm sitting right next to a totally ag plant, and I've been to Arctic, which will be in the presentation and things. So it's good context for this. So I think with that, I'm going to switch to screen share and get the presentation up. Right, if you can just confirm, Tilo, that I've got it's now showing.
Yeah, not yet for me, but might be a delay in your computer.
Yeah. Up yet?
Not yet.
Oh dear.
I'm seeing multiple screens, Malcolm.
Yeah, me too.
Odd. I think it's just lagging because I did Alt Tab to get to the correct screen. Oh, that's going to be a worry if it lags this badly. So it should be up, the presentation slide yet?
Yeah.
No, I think it's frozen on that
yet.
Alt tab.
Yeah, if you can try again, Malcolm.
I think I'll try again.
Yeah, now
Oh.
for a second it worked.
It would do that, wouldn't it? All right. So start sharing. Share. All right, you can let me know when it reappears. I won't be impatient this time.
It's in that multi-screen video again.
Yes.
So basically the title slide is, will ag milling make a comeback? So it's a classic provocative paper that I tend to give at conferences of kind of pushing the boundaries. There's Aubrey, Marcelo, Mosen and Dion from the JK Center, Andre Vian and Mike Mueller from Freeport McMoran, and Grant Valentine from Asenco. Right, is it up yet?
Not yet.
Oh, that's terrible. I hope once it's going, it goes.
Yeah, now we can see your presentation.
Yes.
Yeah.
Yes.
Okay. So there's our title. Just Tula, just feedback if it looks like it's not forwarding. Okay. All right. So the drivers to ag milling. So robustness to operating costs to me is a really big driver because you eliminate grinding media, and so you're less sensitive to varying metal price because you've eliminated one of your significant costs in the process. So the other is CO2 emissions. So the company tells you we're going to reduce by 30% by 2030 or something, net zero 2050. We're all on a pathway. We're all singing from the same song sheet. However, quite standard around the industry is we're increasing energy use, kilowatt hours per ton, and ball consumption by converting to more of a bag mill or run-of-mine ball mill, and therefore pushing up our steel consumption, steel use and steel consumption. So the reality is really different to what we're proposing as an industry. And if we look at what's the CO2 emission from the grinding media side, depends very much, of course, on the ore and the fraction of grinding media and how fine you're grinding. But somewhere 20 to 50% of our emissions are from the grinding media because of the production of the steel and the transport of the steel. They're significant factors in the CO2 emission. And then the embodied energy or indirect energy that goes into the manufacturing of the steel grinding media, 30% of direct energy. So about 20 to 30% reduction in comminution emissions is a viable target by going to ag. And I don't think we can sneeze at that. That's really a worthwhile objective. Is that forwarded to the next slide, Tulia? Ag mill risks and challenges?
Yes, everything is right.
Oh, good. So why don't we just ag mill? Having said, well, it's a great thing. Well, why aren't we all doing it? There's always a reason, of course. The original reason we started with ag milling and converted to SAG and then high and ball load is the sensitivity to ore variability. So the rock I'm holding, how competent is the rock that forms the grinding media? And if it's too competent, you overload, you can lose your grinding charge. If it's too soft, so you can swing between overloaded and underloaded. And at variable feed rate, sensitivity, the pebble discharge rate varies a lot depending on the size, distribution, and competence. It varies with SAG milling, but it's more sensitive in ag milling. The other thing is it naturally produces a fine product because there's a lot of abrasion. Those pebbles on the right that are wearing out, they produce really fine, sub-100 micron by abrasion. So uptake barriers, can we predict the performance reliably? And when I look at putting in an ag mill somewhere or speaking to someone about putting it in, well, we're not sure. Should it be this size or that size? How sensitive to variability? What's the rock going to be in 5 years' time, 10 years' time? Will it still be suitable to an ag mill? So our models in trying to address this, so I'm motivated from a research, development, design perspective to get these implemented in the industry. The models lack transport through the mill and out the discharge system. There's one lumped parameter that's database mainly based on SAG milling. And the dominant abrasive breakage is not in things like impact dominant modeling based on, say, drop weight test style modeling. And the dynamics of the process, so the variable dynamics as the feed is varying over time, minute by minute, 10 minute by 10 minute, day by day. How is this mill going to vary rather than the average? The variability is really important in understanding the process. And it's a risk justifiably seen in the industry saying, well, if we just fill it with balls, it's more stable, which is true, but not fully true. So what are uptake barriers going to the feed variability, characterization across the ore body? How is it going to vary over time? And are we characterizing it in a way suitable for understanding ag milling? So we've got two one, we need to characterize it more than the other. We need to characterize it in a way to understand, for example, the abrasive side of it. But there are many successes. There's the 22 megawatt ITEC Boliden mill. There's the whole bunch of Boliden mills I mentioned, been going for 70 years. LKB, many more in Scandinavia, Olympic Dam in Australia, just to have a nod to my home country. But there's something interesting. If I look at LKB, bottom left, they have a separate bin, which they separate the coarse and the fine. And they can use that for controlling the balance, which they do. ITEC has that big A-frame feeder so that they can distribute material across between the two parallel mills and get a more stable feed coming in. Plus, it's not in the photograph, but on the mining side, it's like every daily meeting is, what's the blend you're sending? You can't be out of spec for the ag mills. So it's not just grades, it's actually competent spec. And they're right on top of it. And the bottom photograph with Mohsen and I is one of my greatest moments in my research career, is we control that mill to 21 plus or minus 0.1 megawatts for 3 hours, fully ag. And that's just amazing. And that was to do with the fact that they control the blend from the mine and they control it at the stockpile. So yes, you can have stable feed and stable production. So new designs, this is where Freeport came in asking for advice on putting a really big ag mill in. And as they made the pilot plant longer, you get the power goes up, the tons per hour go up less, not proportional to the power, and the P80 goes down. So this is well understood that as you make the mill longer, the residence time goes up and your power goes into making a finer product rather than more throughput. So you get some increase in throughput, but also finer product. So where do you want to be on that intersection does dictate your mill length. And the mill length, then adding power by just adding mill length is not a linear increase in feed rate by any means. And this is where they came to us with queries about it. So they've eventually gone, because of the uncertainty of that and the discharge, pebble discharge, they're doing aggressive crushing, fine crushing of the pebble recycle, which is an excellent thing to do. They've gone for 2 mills. We weren't able to answer these questions, and in the brief time we had a look at it, trying to extend our models. Another one I did, and this was with Marcelo and a PhD student, a master student, tabarite ore that there's no ways you should be able to ag mill it. Everyone knows that it's too soft. However, you just need to have sufficient of the competent intersect layer, so the interface layer, to get enough rock in the mill. So you can see the left, absolutely fine. The right, not enough rock in the mill. It just completely grinds out to sand. So yes, it's possible, and it is a lower size specific energy than the ag milling, but you need to control the feed. So if you don't have that handle on your feed, you've got a soft feed, you're going to run into trouble. So I see to uptake, being able to predict what your circuit is going to do is a real key to uptake. So if you're going to predict the design of a mill circuit, production and mine planning, daily operation, that I indicated at the beginning, that's one of our major risks or barriers to uptake. And the other is the dynamics. So the control, the hour-by-hour control. What is the ore type changes? Dealing with surges coming in, with the load going up and down, content changing in the mill. What if I increase pebble port size? What happens if I'm more aggressive with a recycle crusher? And the high overall equipment effectiveness, you want to make sure you can push your mill to drawing the full power and getting the full use out of it while stabilizing the product. And all of this it's kind of a dream in mineral processing when we're varying the input. So it's not actually possible to have a completely stable output, all aspects stable when you're varying the input. You've got to choose what you're going to vary. So you could go for a stable product size and vary feed rate, for instance. But the more we understand blending, for instance, the coarser or more competent with the softer, and can maintain that balance within a window. It's not a point. So it's not a PID loop within a range. you get this amazingly stable operation. So it's quite interesting. You can be 20, 30% around a midpoint, and your mill will be stable. And you drop off that, and suddenly it takes off. It either loses throughput or fills up or becomes super fine. So there's quite a wide window you can work in. So how do we de-risk this? So what are the essential subcomponents we have? Well, the feed. And the feed varies. So what happens in the mill? We've got breakage with impact, we've got attrition, we've got slurry, grinding between the balls. So we've got this whole grinding action that we really want to emulate in our models, not have some backfitted rates model. We actually, to understand and predict this reliably, we need to understand what's in there. And that competent feed greatly dominates the content. Then the transport, which we'll come to next with Guillaume. How does this transport down the mill? I've got some great photographs in the ITEC mill I presented in the previous SAG conference of, as we changed the filling, we got a different size distribution down the mill. So it was changing with the filling as it went from 20, 28, 35% filling. It changed the content in the mill. The feed was in all cases equivalent. So the content is not well mixed. The discharge is completely different to the feed end. So to have success in modeling this, and definitely to have success in modeling dynamics, we've got to have a transport model where the model sees the change in content down the mill and knows by size the probability or rate of transport. And then, of course, discharge, which is an independent function, independent of transport through the charge. How does that vary as I change the design, as the percent solids change, as I change the mill speed, so on. So I can really break down the mill, and that's what we've endeavored to do, or we've done, but it's a not completed model. So large rocks evolve through abrasion and chipping, competent fraction dominates, content is not well mixed, and dynamics over time as the feed varies, like the graph on the right. How is that varying as we were bringing that mill into stability, into a state of stability, and slowly tweaking the feed? And these bits in the box are all lacking in standard SAG mill models. So what are the building blocks? Abrasion breakers. We've developed a test which we've got at the JK, which is purely abrasion, or as close as we can get to it. Unfortunately, it uses a few hundred kilograms. So this is not going to be an ore body characterization test. However, if we can characterize into classes, we could test, say, the 3 major classes. Our objective is to move it into a small scale test, but we're not there yet. Mohsen and I have worked on this with multiple students as well. It really needs a big push on the research side. Incremental damage, breakage, a lot of work done. Marcelo's group, I've done a whole lot at the JK. We have a standard methodology, published methods of incremental damage where the rocks will slowly weaken and then break. Multi-component impact breakage, where you've got different ore types. What's the probability of breakage? So this is a cumulative distribution of fracture energy. And Marcelo, coming out of the Utah group with Peter King, brought this to us, and we're using this strongly now in our modeling. You get a distribution of strength per ore type, not just an average. And the AG mills are more sensitive than SAG to that. And the transport graph at the end, that will link to Guillaume's work on transport through the mill. Then I refitted just a discharge function. And it's rather different to the bulk one we fit at the moment, which is transport through the mill and out the mill all in one function. It is really different and completely different rates out through the grades.
Jag kan gå in och hitta gamla fakturor.
Oh, someone needs to mute Magnus. And all of that we've put in a dynamic mill model. So this is what I did with Ben Bonfils, then later with Dion Weatherly. And we look at transport through the mill, the breakage function at the top into body and abrasion, transport down the mill. You've got an advective bulk motion, got a diffusion, granular diffusion function, separate discharge. So there's your mill, comes out, will recycle maybe via a crusher or just to recycle back to the feed. So we have that, a fully dynamic framework running that. And Marcelo's gone one further with that microscale population balance model. Complex diagram, but I'll just go In the front, you have particle properties, individual particle breakage. In the core, we have energy application to the individual particles, the rate and probability of application. And then iterate to get a mil content, and then out of it, predict a product. So this was actually done with some DEM steps in between with Rodrigo. And this is fully predictive. This is not backfitting of rates. This is, I measured the ore properties, I did a simulation, I got a product. And I did the test work and I got a product. These are amazingly good. So there really is a viable capability of doing this. This is a slow process in here. So getting it to be an online fast model becomes the challenge. This is work I did originally with Ben Bonfils, the early version of our dynamic. You see the top left is the contents evolving in each slice of the mill. And we see the cyclone overflow P80. We started with an empty mill and filled it up. And you see the sump level in there, that's in that circuit I was showing, and then the P80 in each slice. So there we're evolving content in a mill, and there is no convergence. If I give it a stable feed, it will get to a stable content. If I vary the feed, it will keep varying. So upgraded mechanistic ag model. I've got a whole list there, which I'm not going to read through, but de-risking design, I've been looking at flexi circuits for many years and really having a circuit where I could put a screen up front, take a split to a crusher, take the oversized to an ag mill, link to a pebble mill, pebbles to feed the pebble mill, and the rest recycle, possibly to a variable splitter waste sorting, maybe an HPGR or another crusher. I couldn't simulate this except in a kind of conceptual level. And if I look now, what would I need to do that? The upgraded ag model, more thorough ore characterizations. I'm working with GeoPura, I'm in the company. That looks like part of the information we can penetrate into the ore body. Precision rolls crush, I'm doing with Shuja, who's also on the seminar. And well proven for fine breakage, still lacking abrasion into the ore body. Feed control. So you've got a dynamic system and you can test feed control systems on it. So you need a dynamic platform to get all these dynamics in. But the good news is the GCC has come to the rescue. He's going to. So there's the GCC. How about joining the team? And down here, I've got Disseltech. And we're working with a new open source dynamic platform developed on EU funding to put an open source base and then a funded base with our models inside. Of course, we need funding to put them all in and have a truly dynamic platform with dynamic models in it. And that's where we're aspiring to go. And then we can look at the dynamics of a process. And our specific initial target is to get the AgMill onto that platform. So I hope that was fascinating, interesting, and fun. So we won't take any questions now. I'm going to hand over to Guillaume to take you on the transport part of the presentation.
Thank you, Malcolm. This was indeed very interesting. All right, let me just share my screen. Let me know when you guys can actually see it.
I'm seeing it. That's good.
Yeah, we can see it.
All right, excellent. Well, thank you all for being assisting to this seminar. I am Guillaume Chiasson from SGS, working from the Lakefield office in Canada. I'm here today to present you the work we've done on a pilot study to look after rock transport rates and ag milling. I want to thank Malcolm, of course, to allow me to be a part of this research project, as well as André Vien from Freeport-McMoRan, who has founded this research program. All right. So over a few years, Freeport-McMoRan has done extensive piloting here at SGS as part of a large previsibility study. We've looked at multiple grinding circuit configurations at pilot scale, including ag milling, HPGR used as a pebble crushing, pebble milling, SABC as well, single stage ag milling, whole bunch of circuits. And among all this, some unexpected results occurred, such as material transport issues in pebble milling, as well as the impact of ag mill aspect ratio that Malcolm was talking about a bit earlier. Having a longer mill didn't necessarily mean a higher throughput, but rather a finer product. And this highlighted the need to better understand rock transport in and through an ag mill. So 4 pilot plant experiments were designed to meet certain objectives. For instance, we wanted to try to measure the residence time of rock particles through the mill at different size classes. We also wanted to measure the in-mill transport rates independent of the mill discharge. From these 2 measurements, we could then calculate the great discharge rate of the particles. To do that, 4 pilot plant experiments named as T1 to T4 were done. We tested 2 different mill filling, a low mill filling of 25% and a high mill filling of 35%, as well as 2 open areas, a low open area and a high open area of 3.5% and 7.1% respectively. This work was done in a 6-foot diameter mill by a 5-foot long mill, all fully autogenous, obviously. The pebbles were all recycled back in the mill with no crushing. The idea was really to study the transport of coarse particles. And we were using 3-inch grates, so 76 millimeter in the mill. So we essentially had 2 main experiments. The first type of test we did use, we called it the residence time tracer test. In this test, we initially used painted pebbles as tracers. We used 3 classes of particles with 50 tracers each. We had a fine class of 19, 25 millimeter, medium class of 31, 51 millimeter, and a coarser class of 51, 76 millimeter, which was right below the grate size. So the particles were obviously still able to get out of the mill. So at steady state, we were adding 1 size class of tracers in the mill. And because it's a pilot mill, you know, the discharge is fully accessible by operators. So the mill the mill discharge was discharging on a 48-inch screen, and we could manually recover the tracers as they were discharging on the screen. This was all videotaped, so we could accurately determine the time of the particles that discharged, and the time was recorded. But unfortunately, not all tracers were recovered initially. As we can see on this picture there, all these tracers, which are from the 51, 76 millimeter size class, were all green originally. We had 3 to 4 layers of paint on each tracer, but as we can see, the paint didn't last very well. And for many of these tracers, only a few little pixels of green paint was left on them. And also, unfortunately, a lot of the pebbles got destroyed or half ground in the mill. So we recovered for some of them only pieces of tracers. The other thing we were doing at each test is we did a full survey around the circuit, and the ag mill load was dumped and analyzed at the end of each tracer test. So starting on the second test, we've replaced the painted tracer by ceramic balls. We do have ceramic balls here to use as in different grinding applications. So we did use the same 3 classes, 19, 25 millimeter, 38, 51, and 51, 76. But as we made the coarsest size fraction, we realized that this size was actually made of 2 distinct classes of balls of 5163 and 6376. So we've decided just to use that coarser group and divide it in 2 subgroups to see if we would get additional information. As we can see on that picture there, we can see the screen and then the yellow operator on the top right of the picture, and we see a middle-sized class tracer there. And we have another picture here with the small 1925 millimeter tracer bouncing on the screen. So the second test we've done is the in-mill tracer test. In this type of test, we did only use 2 size class of tracers with 20 tracers each. We had 5176 millimeter size class, so tracers that were near size the great, but smaller than the great. And we had larger tracers of 102 to 127 millimeters that were obviously coarser than the great and couldn't discharge out of the mill. So between 2 to 4 minutes before the actual ag mill crashed up, these 2 size classes were added to the mill in 10 seconds intervals, which slightly disturbed the mill, but it wasn't so bad. And we let the material to tumble in the mill for a few minutes, and then we crashed up the mill, got inside in the mill, and then took pictures of the tracers like we see in this case. And then we measured the distance between the discharge grate to the center of each tracer that we found. And then all the visible tracers were removed out of the discharge. The mill was slowly rotated just to expose new lifters. We got back in the mill, make the new measurements, and this was repeated until all tracers were found. And we can see another picture on this slide here. All right, so now if we look at the results of the through mill residence time, so this is the particles that got out of the mill that were recovered on the screen. What we see on this graph is the results or the distribution of the residence time of the particles for the 4 size classes, the finest size class in blue, the medium size class in orange, and then the 2 subgroups, 5163 and 6376 millimeter in yellow and green. This was done for the second test at 35% mill filling and 3.5% open area. And if we look, for instance, at the median of the 3851 size class, for example, we see that it took 19 minutes as a median for the particles to discharge. What we can see in that particular test, there was not that much difference between the different size classes. They kind of overlap on top of each other. Now, if we look at the results for the third test at 25% mill filling and 7.1% open area, what we can see, first of all, is the median of all 4 size classes is much quicker. I mean, they varied from 8 to 11 minutes for the 3 courses size classes, and it was 14 minutes for the finer size class. So it's much quicker than the previous one. And if we look at the results from the last test we've done at high mill filling and high open area, we can see here again that the median of the 3 courses size classes didn't change much, but the finer particles were greatly affected by the higher mill filling in this case, and it discharged more slowly than the coarser particles. If we look at the impact of mill filling on the rocks just below the grade size, so if we just look at the rocks of 5176 millimeter, we can see that at high open area, the mill filling didn't impact anything really, because the 2 curves are essentially overlapping, at least for the coarser particles. It's not necessarily true for the finer particles, but for the near grade size, it didn't have too much impact. If we look at for the low open area, then the story is different. The low mill filling resulted in particles discharging a lot faster out of the mill than at high mill filling. That seems quite obvious from this graph. If we look at it from the open area point of view, so at high mill filling, 35% mill filling, a higher open area resulted in particles discharging a lot faster out of the mill, which seems to make sense. At low mill filling, though, we've seen the same impact, but the difference is not as big. So the open area, yes, helps, but the influence is lower. Then the results for the in-mill transport rate. So those are the particles that we've added to the mill right before the stoppage of the mill. So what we look here is the distance traveled by the rocks from the feed end on the left-hand side of the circuit to the great end of the mill, which is on the right side, represented by the dotted line here. This results from the second test. We see the coarser size fractions in red, and near great size particles in green. What we can see here is the test was probably stopped a bit early because most of the particles had not traveled that far through the mill. However, the coarsest particles, about 40% of them had traveled from 0.4 meter all the way up to 1.3 meter, whereas for the finest size fraction in this case, most of the rocks didn't travel more than 0.4 meter. There was one rock that got all the way up to 1.2, but seems almost to be an outlier. If we look at the results of the third test at low mill filling and high open area, well, it's the other way around, where in this case, we've stopped the test a bit too late, because we can see a lot of the coarsest media as is kind of within the last 30 centimeters of the mill. So but we can see though that again, the coarser media travel faster than the finer media. And if we divide the 51-76 millimeter size class into the two subgroups we were discussing a bit earlier, what we can see is even more interesting. In yellow, we've got the finer part of that class, which did not travel much compared to the coarser ones. And the coarser 63-76 millimeter particles has traveled pretty much as the very coarse media. And if we look at the results from the last test, well, we kind of can conclude the same things, with the coarser media traveling a lot faster and further in the mill. Now, if we express the test results in terms of particle velocities, which we see in this case, we see the velocity of the particles to discharge out of the mill. I'm not going to go through the calculation details because it's a bit tricky regarding the discharge, but nonetheless, what we can see here is the finer particles the velocity of the finer particles is much more slow than the velocity of the coarser particles. But this is the through mill velocities. If we look at the in mill velocities, which are represented by the two additional curves here, what we see here is that the in mill velocities of the particles is much higher, but also and again, the coarser particles are traveling a lot faster in the mill. This is another way of looking at the results, where we look at the velocity of the particles on the y-axis versus the particle size. In this case, for the test T4, which was done at high mill filling and high open area, what we see for the in-mill particle velocities is that the velocity at slurry size, fine size, tends to drop a little bit, and after that it increases with particle size to reach very high velocities for the very coarse particles. If we look at the through mill velocities, so the particles that are actually traveling through the mill, being picked up by the grate and being discharged and getting out of the mill, we see that at fine size, the in-mill velocities and the through-mill velocities are kind of similar. And there's that similar shape of curve with the velocities increasing back at the coarser size, but it obviously doesn't increase as fast as the in-mill velocities. Now, by looking at the difference of the two types of velocities, it's not quite direct, but anyway, this is one way to look at it. We can see that third curve there in blue, which is what we call the grate discharge velocity. So it's actually the velocity of the particles to get to the grate, but then to be picked up by the grate and to discharge. And what we can see in this case is that there doesn't seem to be a big impact of the grate discharge velocity by size up to a certain point, after which it drops quite rapidly to essentially zero once you reach the grate size. And if you zoom in that grate discharge velocity curve, what you get is essentially this. And for those who are familiar with the JCase and Met discharge model, that may remind you something. Then if we go back to the in-mill velocities and we compare the in-mill velocity of the test T4 and T2, so the same mill filling 35, but the different open area, we can see that the lower open area at the lower open area in yellow here or orange, the in-mill particles velocity is less. Same kind of conclusion for the through-mill velocities, although at the finer size, it seems to be relatively similar. And then I think I'm running out of time here. So let's conclude this quick. So surprising conclusions. Well, the larger particles are moving faster in the mill, whereas we tend to think normally that the fines will essentially bypass the mill and the coarser particles are the slow guys in the mill. The slower transport rate for small particles exemplify a higher mill filling. There's a clear influence of open area through the mill residence time. At low open area, the grade discharge is definitely the bottleneck, and all particles are behaving more or less the same through the mill residence time. However, at high open area, it's the in-mill velocity that becomes the main driver, and therefore the larger particles will discharge a lot faster out of the mill. So this project led to significant better understanding of the transport of the particles through and in the mill by separating the two mechanisms. It has obviously an impact on the better understanding the pebble buildup and the pebble discharge out of the mill. And I really want to thank you, Malcolm, but also Freeport for making this experiment possible and allowing us to publish these results. So that's it for me. Hello, can you guys still hear me?
Yeah, well, excellent. I think Malcolm may have been having a technical difficulty. Thanks, Guillaume. Maybe Aubrey, if you're ready, you can take over for the last part of the presentation.
Thank you, Marcelo. I am ready, but I'm not being allowed to share.
I think you are, Aubrey. Maybe you can check.
I can now share. I wasn't a few minutes ago.
Yeah, sorry, it was me that was still sharing my presentation. Sorry.
Yeah, I think so.
Yeah. So what I'm going to present this afternoon or morning, depending on where you are, or evening, is a presentation that I gave at the SAG conference on behalf of the whole host of people. The theme was the AGNU design for low competency ores, and the co-authors for this paper were Sandile, who should be in the audience today. I haven't looked at a participant, and then Malcolm, as well as Talita Bell from Tronox. So this is the work which was done at Mintec using the pilot plant work and other mills that they have. The motivation for this work is that Tronox are in the mineral sands business, and they have been mining the mineral sands for many years. However, they want to expand their mining operation, and because of that, they'll be building a new plant to accommodate the new ore that they have found. This ore that they have found has very low competency, and you will see as I go on in the presentation what the quantification of that resistance to breakage numbers would look like. The risk of using standard techniques for this ore are that, one, you would not know what the product particle size distribution would look like, because it is very different, particularly in a continuous system, to what we've encountered in many operations before. The second is measuring the specific energy using any lab-based techniques without cross-checking would be highly misleading for this particular ore. The third part is that the rock load within this incompetent ore is variable, and also you would not know whether you are able to hold the load. There is actually doubt if you can build up the load of coarser rocks with this material. Then the other point is, if you were to treat this material in closed circuit, the models cannot help you to predict the circulating load accurately because it behaves very differently. And then the last part is it is very difficult to work out what a mu length would be. And this touches on the previous presentation where they did residence time studies. You wouldn't know how long the material would last in the mu to a size that you want. So the inference of whether you have a long mu or a short mu is very hard to predict from our conventional models. Based on that, a number of studies were proposed. And this work was done for Tronox, who currently are using an ag operation to process the ore on the neighboring plant, which is called the waste plant. So because of the new ore that they have found, they are in the process of designing a milling circuit. Now, all those questions and comments that I gave previously are things that were put on the table. If they implement the ag milling, which is preferred because they are using the same technology on the waste ore, what would be the length of the mill? Would the mill be able to hold the load? What would be the circulating load? What is the competence of this rock to act as media? And because of those questions, they commissioned this study. Just a bit of a background on the ores that we are talking about. This picture shows you where they are mining in terms of mineral sands. You can see the mining method is mainly by dredging. But if you look at this particular picture, you will see the waste zone that is overlaid by feldspathic sands. And you can identify this because it's got a bit of orange color, and that would be the material there, interlaid by the red Orion sands, which is that material. But the east material has predominantly this layer than that orange layer. So this orange layer has a bit of competent material in it, but that reddish material that you see in there has a lot of incompetent material to act as grinding media. Just to give you an idea, when I speak about incompetent material and competent material, I'll take you to this particular graph or table here. You would see in this table, if you just look at the A by B number, for those that are familiar with the drop weight test results. If the A by B is low, then it means your ore is very competent. It's very hard to break using impact. If your A by B is very high, it means your ore is very soft. Now, these numbers here we have A by B number of 565, 962. Those of you who are familiar with the JK drop weight test table, they are not even in the table. They are too soft, such that we've not encountered these numbers before. So these are extremely friable and soft. The waste ore, or the waste reef ore, which you see here as 312, is more competent than this. But even when you look at that JK drop weight test table, this is actually classified as very soft. So if this is very soft, I would shudder to think of what we would think of the other numbers that are above 500. If you look at the resistance to breakage by abrasion, which is this TA, these numbers are very high as well compared to what we've encountered in the database. And for those who are disciples of bond, you can look at the bond number here. For the East ore, you will see the bond number less than 4. And most of you would comment that you don't usually see bond numbers that are this low. At least the West Mill, which has a bond number around 8, we may see those numbers. So this tells you the complications that one would face to execute a design with these breakage characteristics. The first test that was proposed and carried out by Sandile, who is in the audience, is the rock survivability test. And the test is carried out by charging your rock survivability mill, which is this one here. You can see material is sized into various coarse fractions. Then you charge into the mill at up to a particular volumetric feeding. Then you run the material for a period of time. You open, you discharge the material, resize the material, remove the fines, charge it again and top up. For this particular material, the test was terminated at the first stage because the charge was found to be below 7%, which is very low. Assume you are coming from, say, 35%, and you run one cycle and you are below 7%. It tells you that the mill can't hold the material. The material breaks very quickly. And you can see the pictures here at the bottom, the fines and what has come out of the mill. There is a very small proportion of coarse material in there. So this confirmed that we would not be able to hold the load in an ag milling operation with this material. But our client and the design company were still insisting that they would like to design a long mill because that test does not talk to what they were doing in the model that they were using. So we had to propose to do a pilot study, and we did a pilot study at Mintech, which has a Rolls-Royce piloting mill. The circuit that was used on that study would be like this one. You can see this is the auto mill, and the material from the auto mill discharges on a 1 mm screen. The plus 1 mm screen would be transported back to the mill using a bucket elevator. Then they have a silo at Mintech where you can charge with the sub 50 mm material, and you draw using a belt feeder. And then we were charging other proportions of sizes manually at a timed interval to meet the required feed size distribution. These are just the pictures of the system. You would see this is the material, the sub 50 mm material from the silo, discharges using that feeder, and we have this belt putting it on the main belt that feeds the grinding mill. What you can see from here is that we don't have rocks. Even after charging the coarser rocks to meet that PSD, you can count the few rocks on that belt. The ore didn't have a lot of coarse material. And this is the material going into the feed chute. And here we have the material discharging from the ag mill. Paul happily sampling that. Excuse me. And then this material here would be the screen oversize being sampled and timed. This is the screen undersize. So the system was very simple to obtain very good samples from the pilot testing. In terms of stability, most of you may know that it is very difficult to maintain stability if you have friable ore. And it was a challenge to reach that, but we perfected the system to a level where we were able to get very stable pilot runs on this particular system. And what you are seeing here are just the conditions, giving us an idea of the stability of our pilot runs. This is just to give you insights on the charge inside the grinding mill. You would see up here that we actually blocked off some plugs to be able to retain some material during the pilot testing, and very little material was left in there. This is in the order of about 11 to 15% fuel level during the piloting. We couldn't go higher than this. At the bottom here, it shows you the contrast with the west ore, where you can see evidence of very big rocks dominant in the charge of the pilot mill, compared to the east mill, which had this sticky material. The discharge is almost covered by sticky material, and then the slurry was always above the rock load. By way of PSDs that we got from here, excuse me, on the left, we are seeing the PSDs for the east ore. And if you look at the feed, that black line there, it's very fine feed. And the red line is a product, the screen undersize. Then the recycle stream, which is a screen oversize, would be that material there in Botswana blue. And then the navy bluish material, PSD here, represents the mill discharge. You can see below 1 millimeter, that the meal discharge is almost identical with the feed that we are putting into this auto meal. On the right, we see a comparative test with the waste ore. You can see this is very coarse, the feed, and then the product is very fine and much closer to the meal discharge than the yeast ore. This already tells you that taking what you do on the waste meal and designing the yeast meal would give you a very different output. The performance between the two, for the system between the two ores would be very different. We did a lot of tests. What I showed there was just an example of 2 comparative tests, but the tests had very different feed size distributions. The navy blue one here, you already saw it, that's the waste ore. Then what is termed the E1651 on the east, which is a bit more competent than the other parts of the east ore, is represented by that blue line there. And then the red line here represents a blend between the what they call the E0595, which is the softest, and this particular east ore that gives you that. And the blend between the east ore and the west ore would give us that black line. So we did the tests with various blends and in isolation, the east and the west ore. What you can see on the right is the ag meal discharge. What you would see is that the east ore blend, which is this red line, is the coarsest of all the tests that we did. And the waste meal product, though the waste ore meal product is the finest of all, the one that had a lot of competent material, reasonably competent material, and was able to build up the charge in the system. This is just the screen undersized product. Again, you can see the finer one is the waste meal and the coarser one is the east meal blend. So this tells you that if you are aiming for liberation, you would not liberate most of your material if you are running it with the yeast meal ore at those conditions that we did the test. Just to give you an idea of the energies, because this is an important input in design, if you use the yeast ore blend alone, you would see that they would require the size-specific energy of about 1 kilowatt-hour per ton. The yeast ore and waste ore blend, they would require the 1.5 kilowatt-hour per ton. And then the yeast ore and the yeast ore and waste ore blend would be 0.9. Then the competent yeast ore would be the 1.5 kilowatt-hour per ton. And the waste ore on its own, it would be the 1.5 kilowatt-hour per ton. Now, this is important because they were designing this using a system that has steel bores in and getting the specific energy. So they designed specific energy before these tests were in the order of 5.5 kilowatt-hour per ton. You can see it is way higher than what you would encounter when you use the pilot work, which is a similar system to what they are designing. And this gives you an idea of the sub-212 micron material. All the tests we did were in the range of 50 to 60% passing 212 microns. And in this particular system, the material above 600 microns would represent a loss in terms of the recovery of zirconia, which is a key mineral. The other part that I wanted to point out when we are on this table is look at the circulating loads when you run with this material. The yeast ore blend alone would be nearly 50% circulating load. This is catastrophe for screen. A screen does not work well when you have such high circulating loads. You require circulating loads that are below 25%. Having circulating loads way higher than that 25% would present operational challenges. But look at the waste ore here compared to the other blends, 12%. This is where the screening application would be very happy compared to the other 3 systems. So all these put together were sending warning signals that the design would not be able to meet what they were looking for. So they did a revision on the design in terms of the length of that ag mill and in terms of the specific energy, but there are still other issues like holding the load in your ag mill. These tests demonstrated that they would struggle to do that, but did not tell them what to do in order to hold the load. This is the tests that were done using a laboratory-based mill with different steel loads at different energies for the initial design. You can see they were having energies of 3.5 kilowatt hour per ton, and in some cases, the lowest was 1.5 kilowatt hour per ton, and they used the higher value of about 5 kilowatt hour per ton with a safety margin to design the plant. This is catastrophic if you compare to what we just looked at a pilot plant, which is much more closer to reality than this. The second part is these tests cannot give you a prediction of whether the mill will hold the charge or not, because you put the charge is defined by your steel balls that you put in the system. By way of conclusion, for low competency ore, an ag mill performance will be very sensitive, the feed size distribution, and the feed competency. So you need to assess the feed competency to be able to design this correctly. The second conclusion is that using lab-based systems with steel balls in are highly inappropriate for these ore types. They will be highly misleading, and they do not give an indication of the suitability of the charge to build up in your system. So beware of these tests that do not resemble the system that you want to construct, and the model cannot take these as inputs to predict what an ag mill would do. That would be the end of the presentation. And I wanted to say this is the real design work that Malcolm, Sandile, and I are participating in. The second phase is to test actually what can we do to build up the load by seeding either pebbles or using ceramic media, and that's the next phase of testing. Thank you.
Thanks, Aubrey and Guillaume. I didn't have bad connection earlier. I was fetching coffee. I know we've used up our full time. We've all been a little bit more relaxed than at a conference of keeping to time. So we're happy to take questions. We understand if you need to drop off to your next appointments, but we're happy to take any questions over the next 5 or 10 minutes for people who have questions for us.
I think Marcelo has a question.
Yeah, so while people are warming up, just to make a short comment. Now, fantastic presentations there, but really just take advantage of a minute of Aubrey's time. I think it is, I think also a great conclusion that you get is, yeah, I think in very certain situations, I think people insist in doing sag milling pilot scale tests because of they are not quite sure. But I think egg milling, especially for very unusual ores, isn't it? I think we're far from being confident at the bench scale. So it is a great case to show that the easy question is no, isn't it? If you want to go to bench scale. But if you want to yes, you have to do a little bit more work or quite a bit more work. And I think fantastic example there. It really talks a lot with the type of tabarite iron ores that you know well. We work here in Brazil. I think it would be a fantastic opportunity to apply. But of course, there's a lot of cold feet around that because you have to do the pilot scale. But congratulations, all three presenters.
Thanks, Marcelo. Yeah, that really loops back to the beginning of, I hope it's really illustrated through these presentations where the uncertainty is. And if someone asks me now, what test work for pilot mill, I give them a bunch of, for an ag mill, bunch of test work, and you've got to pilot it because you can't fully answer the questions yet. So we are in that position, and it is the big pushback to installing ag milling. But as Marcelo said, that taborite was really encouraging. But the cold feet and the barrier is there. We need to overcome that if we're going to address the drivers I put in right at the front. Any other questions out there?
Look, I'll jump in, and probably more of a downstream question for all of you, and you could probably preempt it. But obviously we focused on breakage, focused on P80s here. I'm wondering what work or what you can tell me about the resulting PSD and cyclone overflow. And if anyone's looked at how the breakage or selective breakage might be different in an ag mill versus or ag ball mill versus a sag ball mill. Is it likely to be similar, or do you think there's any advantages?
We certainly got a different distribution. So the distribution is markedly different from the two operations. And Aubrey, you can take over.
Thank you, David. It's a very insightful question, David. Even if you go to SAG milling at different proportion of steel balls, the PSD that you get out of this is very different, because we've tried to actually put a lower ball load and an intermediate ball load. The PSD is very different. And in their case, the SAG mill with about 6% ball charge had the most unliberated material compared to even the ag mill. The other test that I did, which was not part of this suite, is we were running an independent test. We closed it with a screen. We found that the liberation profile with a screen was much better than that of the cyclone, even if the product size from the cyclone looked finer than the screen, which was telling that sometimes we use a wrong classifier because we are targeting fineness but not liberation. If we use a correct classifier and push the material to just where it liberates, it actually gives us a better solution.
It's actually critical in this, or because they use fine screens. Otherwise, they slime and lose product.
Okay. And I guess the other part was looking at that data of Aubrey's is, you got so much fine in the ag mill feed. From a circuit perspective, does it not make sense to pre-screen or put a scrubber in just to get rid of that sort of 70% material, and then maybe secondary crush would be something different with the course?
David, you hit the nail on the head. We were actually proposing a different milling technique, but the client is adamant that they want exactly what is next door. If we were asked what is the solution for this material, I think our departure point would be very different where we are.
Okay, thanks, David. Lawrence, you have a question.
Hi there, everyone, and good to see you, Malcolm. Good to see you, Aubrey. It's just a comment and a question here. Lawrence from Mintech here. So the first comment is thank you to Aubrey for calling the Mintech pilot plant here Rolls-Royce. And I think there it really was fantastic work that was done by Sandile and his team. And really just a comment on the value of having a research-led design. Often you have the engineering company come to the researchers and inform us of their models and how their models can inform a better design. But in this case, this was a useful case in which we could actually demonstrate that actually the value of the research would have informed the design a bit better. The second one is a question for Malcolm, just in terms of your the case that you're making for the ag milling and so on. How would you perhaps make the case in the case of having a high aspect ratio mill in which really impact is quite dominant? What would you do in terms of the modeling, and what do you think the capabilities are in the event of making a case for ag milling in that case?
The tendency with ag mills, of course, has been to have a lower aspect one, so a longer mill. But if you look at the Arctic one, it's 38-foot diameter, so it's 11-meter diameter. And it works just as we see with the other ag mills. There's not sufficient energy to dominate the impact breakage. So that photograph I showed was inside the high-tech mill, and it's a relatively soft ore. It's 10 kilowatt per ton to produce a product of minus, I think it's 110 micron, 120 micron. And still the pebbles survive because there's a competent enough fraction in the feed is the secret to that one. So I don't see that as a challenge at all. It's not a high aspect, but it is a big diameter. So they definitely still survive.
Okay. So I guess in that case, it would be dependent on the competence of the ore. Thanks, Malcolm.
Yep.
Lawrence, just to answer your question, I don't see any distinction between design companies leading the design or research led. I think if we work together, we can find better solutions. So it's finding those linkages where design companies and researchers have a synergistic relationship who achieve much better solutions because we may understand a lot more about material characteristics than what they would in a standard design. So if we put our experiences together and the new models, for instance, Marcelo's new model and Rodrigo, will achieve much better designs than what we currently have. And also the operators being bold enough to allow designs that look different to what they are used to. Thank you.
Indeed. Thanks, Aubrey.
Guess we've run quite a bit over time now. It's great to have the interest. Most people still sticking on. So maybe we should close off there. And thanks again, Tulio, he's our formal host.
Yes.
Pleased to have people on board, and thanks a lot, Guillaume, for joining in this and the great work you did as part of this, which is very exciting from a distance.
Yes, thanks, Malcolm.
Right, everyone, we catch you at the next seminar. Have we got one more this year or not, Tulio? I was trying to remember.
No, I don't think so. We don't have in December, so maybe January. Yeah.
Well,
We
you're just going to
check
have
it.
to put up. You'll have to put up with having Christmas holiday or something instead of a seminar. All right. Thanks, everyone.
Yeah.
Cheers,
Thank you.
Bye, everyone.
Cheers.
Bye-bye.
Bye.
Great presentation.
Yes.
Thanks all. Bye.